Thank you. Hi, everyone. My name is Arpit. I'm from UCLA, and I'll be talking about sensing and controlling symmetry-broken states in light matter hybrids. Before I start, I would like to thank you all for hanging in till the last day and last session. So here is a brief outline of what I'll be talking about. So I'll start with what's the role of photons in quantum sensing and engineering quantum states. And then I will discuss the role of non-trivial wave function windings in quantum information and quantum materials. And then I will share two of our recent works in which I'll talk about probing symmetry-broken states using quantum metric or photonic states. And then lastly, I'll talk about the optical control of non-equilibrium superconductivity in flat band systems. So here's a brief overview, what I'll be discussing in the next few minutes. So I'll introduce a new protocol that we have tried to come up with to do sensitive probing of non-reciprocal responses. And we do it through a cross-cavity device where we have two cavities arranged in a cross geometry, and the sample under examination comes in the center. And we do a quantum tomographic process to execute the measurement, and I will tell you how this works. And then what I will do, I'll tell you about how non-equilibrium superconductivity unfolds in flat band systems, and I will do it through the context of gap enhancement. So there's a sweet spot of frequency ranges where if we shine light, we can actually enhance the superconducting order. And I'll tell you that the flat band systems are a little tricky, so we need to go and do some special stuff to excite virtual transitions and see how things unfold. So I'll start with photons for quantum sensing and engineering quantum states. So we all know what quantum sensing is. We actually sense quantum phenomena in some way or the other in everyday science. But when I say quantum sensing as a term, it has some stringent protocols such as quantized energy levels, coherence times, and so on. But people have been doing it for some time. Like we have neutral atoms, trapped ions, Rydberg ions, squids, and superconducting circuits. And there's one method that we are particularly interested in is of NV centers, which are formed, let's say we have a diamond tip and we create a hole vacancy inside these diamond tips, and this hole vacancy acts as a spin qubit, and which is able to detect very sensitive signals such as noise magnetometry, and transverse response to conductivity. And very recently, we have given this new protocol of detecting BKT transitions using NV centers. So now coming to using electromagnetic modes in quantum sensing, again, people have been doing it for some time. For instance, Ramsey interferometry is quite an old technique. People have been using light to control the Rydberg atoms for a long time, and then we have these optomechanical systems to detect signals. Again, one very popular and thing that we are interested in are these ring resonators, where we have these quantum capacitance and quantum inductance. And the nice thing about these resonators is that they integrate very well with the 2D materials, and we have heard a very nice talk from Joel how he detected superconductivity in twisted bilayer graphene using these ring resonators. So now coming to engineering quantum state. Now we have two aspects. One is quantum information science and the other is quantum materials. Now in information science, again, it's been done for a long time. A classic example is of the noon states, where we can use different polarizers to create a special state of light. And it was proposed to form a sensitive device for susceptibility probing. And then we can have reservoir engineering to light. And then again, a classical example of an atom cavity systems where we can achieve maximally entangled states. Now, when I talk about quantum materials, here is a classical example of how we can generate a symmetry-broken state using light. That's the light-induced anomalous Hall effect in graphene. It's been some time it was discovered. And very recently, we have shown how we can use light to stabilize a ferromagnetic phase. For example, we have this material, YTIO3, which is a degenerate Mott insulator and has fluctuating spins. So now if we use terahertz to excite the correct mode, the correct phononic mode, we can now stabilize this ferromagnetic state. So now we're talking about non-trivial wave functions in quantum information and quantum materials. Again, starting with quantum information first, the role of non-trivial wave functions or quantum geometry in general is very straightforward. It comes from the quantum metric, which goes into the quantum Fisher information. Quantum Fisher information gives us the Cramer-Rao bound, which tells us how distinguishable are the quantum states upon measurement. And it's been verified very well. Now, coming to quantum materials or solids, solids have these one element of emergence. So the role of wave function is not limited. It has a wide range of emergent phenomena. For example, here we have the electron motion, which itself is modified by the role of wave function. We have Berry curvature, we have quantum metric, and let's say if we have a wave packet inside a block band, then the Berry curvature gives us the self-rotation of this wave packet, and the quantum metric gives us the spread of this wave packet inside the block band. And this gives rise to a number of phenomena such as topology, transport such as anomalous Hall effect, nonlinear Hall effect, and optoelectronics such as bulk photovoltaic currents. And very recently, I was able to show the role of wave function and quantum metric in generating non-reciprocal plasmons. And I call them quantum metric plasmons because it's a means of generating, passively generating non-reciprocal plasmons in flat band systems, and they're completely governed by the quantum metric in these flat band systems. And most importantly, we have already heard a couple of talks about it, is the example of flat band superconductivity. Now, the electrons in flat bands per se must be localized, but if there's a wave function overlap at different lattice sites and the system is interacting, then these localized electrons tend to get delocalized and gives rise to the superfluid wave, and it's been very well detected, and we heard a very nice talk about it in this workshop. Now, coming to probing symmetry broken states using quantum metric or photonic states. So here's the motivation. So the motivation is that whenever we try to measure a non-reciprocal response, we do not know, or it's very hard to experimentally determine what its microscopic origin is. It can be current, polarization, magnetization, and there are a number of terms that contribute simultaneously. So our aim is to move closer towards detecting microscopic mechanisms, because these measurements tell us details about the physical phenomena which have functionalities that can be used for new technologies. For instance, we have transport measurements. Very simple thing, Hall bar have been used for a long time. It has been giving us very interesting results for a long time. And very recently, people have come up with new kind of transport geometry. We have the sunflower geometry, which have been used to precisely determine the symmetry-dependent transport. And then we have classic source train, very simple setup, and we're recently putting more materials and measuring signals using this source train setup has given rise to this ratchet effect, and ratchet effect then was proposed to be related to neuromorphic computing. So now with this intention, we try to propose a new protocol having this device which has two cavities arranged in a cross geometry, and the sample under examination is placed in the middle. And the working principle is quite straightforward. So we have electromagnetic modes inside the cavity, and how they couple depends on the material response. And the functionality of the device is also very straightforward. When we perform measurement over the photonic states, we indirectly extract out the information about the sample. So let me just explain it a little bit more. So let's say we write down the Hamiltonian for this device. The first term gives us the frequency difference between these two cavities that we have, and these frequencies are shifted a little bit by the longitudinal response of the material. And the coupling between these two cavities is governed by the transverse response of this material. Now, just like any other problem, or most of the problems of quantum information, we can map out this problem on an SU2 sphere and write the Hamiltonian as an effective spin Hamiltonian inside a magnetic field. So the spin comes from the photonic state on this SU2 sphere, and the magnetic field is actually a material response. So here is how we propose that the device would work. We can use beam splitter and phase shifter to prepare an appropriate photonic state, which goes inside the cavity, and then something happens when it passes the material, and then the signal goes out for detection. And here are details. So detail is the following. We prepare a quantum state using beam splitter and phase shifter, and then we allow the state to evolve in time, and then we do the back tracing, and we do the measurement. We understand that since we have allowed the state to evolve, it's highly unlikely that we will get the original state back. So there's a difference between the initial state and the final state, and this difference is given by the quantum metric. Now, this quantum metric has a very important property that it depends on sample properties, and that's captured inside the B. Now, for example, if we have a state that's prepared perpendicular to this B vector, we will have a vanishing quantum metric, and that's shown in the inset of this figure, where we have these bright blue spots showing 0 quantum metric. And if we prepare any other arbitrary state, then these positions of minima and maxima, they shift, and that's being shown in the main figure. Now, the point is that we are now passively able to extract out the sample information by performing measurements over these photonic states. Now, here is a little more realistic result. Let's say we prepare a multi-photonic state, and then if the state is prepared perpendicular to the B vector, what happens is the photons, they prefer to go between the photon population decides to go across the cavities. It just oscillates between the two cavities. And then when we perform a measurement on the probability of these photonic states, we find that a multi-photonic state will show one big peak in the middle. Now, on the other hand, if we prepare a state that is along the B vector, then what we find is that the photons, they decide to be confined within each cavity. And they do not cross paths and do not go to other cavities. And what happens when we perform a probability measurement on this photonic states, we see nothing. So it's a clear signature how we can using the measurements of this photonic state, we can determine what are the sample properties, because this B vector is precisely determined by the sample response. So with this, I would like to tell you what's ahead along these directions. Along these directions, what we plan to do, of course, do some nice collaboration so that this device can become a reality, because right now it's just on the paper, so it's ideal, always works, but we don't know how it will turn out once we make it. And then we want to test different physical phenomena against this protocol so that we know how much the device, at least on paper, performs better as compared to other existing probes. And then we also plan to make an array of this device, which can be used for quantum state preparation, and that can be used to enable on-demand variational parameters that can be used for quantum computing. So now I move on to the last part of my talk, which is about non-equilibrium superconductivity in flat bands. So we know why flat bands are interesting. They're interesting because they're considered a probable route to high TC superconductors. And that's because the TC in flat band superconductors is linearly proportional to the coupling strength. And most importantly, the superfluid weight in these materials is given by the quantum metric. So again, materials are very familiar to all of us. Twisted biographene is the most popular one, where we have superconductivity, we have these domes in their correlated phases, and of course we have the entire graphene family. So now the question that I would like to ask in the next few minutes is that what happens if we shine light on flat band superconductors? So my context is in terms of enhancing the superconducting order by shining light, and how this works is the following. If we look at the gap equation for superconductor, it has two important elements, that is pairing strength and the distribution of the quasi-particles. Now, if we shine light, then we can actually perturb, or we can change the distribution of the quasi-particles, and then we get a correction coming from the light field. And now there's an interesting consequence. The consequence is that if we can somehow decrease the quasi-particle distribution, then we can actually take the superconducting order, superconducting gap higher. And how this happens is because the most important quasi-particles, they lie along the band edge. So if we remove quasi-particles from the band edge becomes cooler, and the superconducting gap goes higher. So, and this has been known for a long time now, and goes by the name of Eliashberg enhancement of superconducting order by shining light. And there has been a renewed interest in this phenomena due to the improvement in experimental techniques, and there have been a lot of experiment on these multi-band superconductors, and the material right now people are focusing is MgB2. And recently it was also shown how this effect would uncover inside a cavity. So now if I talk about flat band superconductors, an interesting thing happens. So firstly, how this works is the following. We need to make excitations within the same quasi-particle band. So we need to break some momentum conservation. We cannot have a momentum conserving process. So otherwise, every process is blocked by Pauli's exclusion principle. So we have some disorder that gives the momentum, and then we have light-matter interaction, and the scattering takes place. Now, if we just try to calculate the change in distribution of the quasi-particles, we find that it's proportional to the Fermi velocity, and Fermi velocity is suppressed in flat band systems, and therefore the dynamics of the non-equilibrium quasi-particles is quenched. So we can't do much if we just do this. But the point is the flat bands are not alone. They always have many bands along, and some of them are remote bands. So what we can do is we can consider higher order processes. Let's say we have a quasi-particle which interacts with light, then gets some momentum through the impurities, and then it again interacts with light. So what it does, it induces virtual transitions. And now, if we have these virtual transitions, we clearly see that, for example, here in twisted bialeographene, we have the non-equilibrium distribution dipping down with light, with light, and then we also see this gap enhancement. Now the main point is that all this depends on the interaction strength and quantum geometry. And why is it so? Here is the reason. So what we are interested in getting the non-equilibrium quasi-particle distribution. And if we just write down a simple kinetic equation, assume detailed balance, we can get the correction to the quasi-particle distribution through the collision integral. And this collision integral can be very easily calculated using Fermi's golden rule. Nothing complicated, and the main player here is the light-matter interaction. Now, we have superconductors. We write down the BDG Hamiltonian, and we just switch from orbital to band basis, and we see unusual things happening. Now, suddenly, the gap function depends on the light. And when we start exploring this gap function, we see that there are intraband and interband contributions. The intraband one depends on the quantum metric, and that's what gives us the well-known superfluid weight in these flat band systems. Now, what has been less explored is this interband contribution, because as we can see that it's linear in the field. Therefore, it's a paramagnetic response which has been less explored in superconducting systems. But if we just look at the light-matter interaction and we just do the usual minimalization, we find that this interband contribution then goes into the light-matter interaction, and now it depends on the interaction strength and quantum geometry, and that's what was giving to this gap enhancement enabled by these virtual transitions. So with this, I'll tell you what's ahead along these directions. So although we have quench dynamics for isolated flat bands, but it might be not as bad as we think, because we know that in superconducting architecture, there's a main source of losses that's non-equilibrium excitations. If it's quenched, we might use it there, but let me be very honest, very ambitious of me to think that. There's a lot of work that needs to go for it. And then one more thing that's very promising, and there are a lot of results that I have, but I won't show it here right now in interest of time, is the cavity-induced superconducting diode effect, where we can break symmetry by cavity, and then we can have a large superconducting diode effect, which is tunable by photon numbers. So with this, I come to an end, and let me just summarize that. I told you about sensing and controlling symmetry-broken states in light-matter hybrids, which are very, very closely related to non-trivial winding of the wave functions. And with that, I thank you. I thank my coworkers and funding agencies.